So today I'm going to show you how to do calorimetry calculations. And the calorimetry calculations are very much like the specific heat calculations that we did last time. It's the same equation essentially. We're just using it in a little bit different manner. So for the equation up here, I'd like you to write that it's the heat of water. So Q of water is equal to the negative Q of something else. And in the case of our example, it's going to be the heat that's being lost by a piece of metal, but it could also be the heat that's being lost by a chemical reaction. And so we assume that all of the heat that's given off by this metal or this chemical reaction is then absorbed by the water that's surrounding it. And that's essentially what calorimetry does, is it measures this transfer of heat from a chemical reaction or from some physical process into water. And hopefully you've watched a few of those videos about calorimetry. You'll also do a lab simulation where you watch a video about a calorimetry experiment. So what we're going to be able to do is expand these chemical or these calculations, these equations, into mc delta T. So this will be mc delta T of the water, and this will be mc delta T of the metal in our case. And so we're going to go ahead and make our list of variables over here. So first we have the mass of the metal. So I'm going to put mass of metal, and that's 50 grams. And it says it's heated to 100 degrees Celsius. That's going to be our initial temperature. And then if we look at the rest of the question, it says it's put into a beaker with 400 grams of water, and the initial temperature of that is 20. The specific heat capacity of the bolt, the final temperature of the water is 22.1 degrees Celsius. This final temperature is the final temperature for both the piece of metal and the water. And that's because all of the heat from the metal has been transferred into the water so that they've reached the same temperature. So to do delta T, we're going to do final minus initial. So the final temperature minus the initial temperature. And so we'd end up with a change in temperature of negative 77.9 degrees Celsius. We're also then given the mass of water. So we'll have mass of H2O, which is 400 grams. And then it tells us the initial temperature of the water, so we can also do delta T of the water. So again, the final temperature of both the water and the piece of metal is 21 or 22.1 degrees Celsius. The initial temperature of the water was 20 degrees Celsius. So the difference here will be 2.1 degrees Celsius. The other piece of information you should keep handy for these problems is the specific heat capacity of water. And this is a constant number that's on your equation sheet, and it's also given in some of the problems that you'll work. But it's 4.184 joules per gram degrees Celsius. All right. So our first equation is the equation for water. So we're going to do Q of water equals mc delta T, all for water. So this will be the mass of the water, the specific heat capacity of water, and the change in temperature of the water. The mass of the water is 400 grams. The specific heat capacity is 4.184. And the change in temperature of the water is 2.1 degrees Celsius. So when I multiply all of those together, I end up with 3,515 joules about. I've rounded that off just for the sake of brevity. So this amount of heat is the amount of heat that was absorbed by the water. And we're also going to have to then say that because the amount of heat absorbed by the water is equal to the amount of heat released, that then the Q of the metal is going to be negative 3,515 joules.